Retina, Part 3. Let's use an example to see how to build a receptive field Kx from summing cosine waves. This is our center surround receptive field with its center component and its surround component. Let's simplify to a one-dimensional space only along the horizontal axis. Then the center component has this profile, the surround component this whole profile, and this is the net center surround profile of the receptive field, Kx. Let's make some room and amplify the profile for better visualization. This is the rough size of the receptive field. Typically, this size, especially the size of the center, is much smaller than the size of the visual field. This receptive field is built from the summation of cosine waves. Here are the illustrative examples of these contributing cosine waves. From bottom to top, these waves have increasing frequencies. These black dashed horizontal lines mark the origin for the vertical axis, which is not shown to avoid clutter. This red curve, for example, is a cosine wave with 3 cycles or 3 wavelengths of cosine waves across the whole image. So its frequency is 3 cycles per image. Cycles per image is sometimes used as the unit to indicate spatial frequency in an image. When the frequency is 0, this red curve is a straight line. And this one has a very high frequency, 39 cycles or 39 wavelengths of the cosine waves across the image. The amplitude of the waves scales with the contrast sensitivity GC, and this wave has a lower contrast sensitivity, and these are 2 examples with even weaker contrast sensitivities. This makes sense because the contrast sensitivity function peaks at the optimal frequency when the wavelength of the grating is similar to the size of the receptive field. If we remove the contributions from higher frequency components, the receptive field becomes larger, since its building blocks of cosine waves have larger stripes or longer wavelengths, and its peak value drops down. Removing 3 more components, the receptive field becomes even larger, and its peak drops even lower. Now let's slowly add higher and higher frequency components and see how the receptive field changes its shape and size. This is by contribution from components up to frequency 2 cycles per image, now up to 3 cycles per image, up to 4 cycles per image, to 7 cycles per image, 9 cycles per image, 14, 19, 29, 39, 44, now including all the cosine wave components. At x equal to 0, all the cosine waves are aligned, so their peak values add up to contribute to this central peak. At spatial location far from the center, different waves have different phase values, so their contributions cancel each other to give almost 0 value for Kx at these spatial locations. So the receptive field size is smaller than the whole visual field spanned by each cosine wave. When our receptive field Kx is modeled as a difference between 2 Gaussians, with this center Gaussian and this surround Gaussian, the contrast sensitivity function Gk as a function of spatial frequency k is obtained by Fourier transforming on Kx. And we again get a difference of 2 Gaussians. Each Gaussian in frequency k comes from one of the original 2 Gaussians in space x. This is because Fourier transform of a Gaussian function is still a Gaussian function. The original Gaussians are Gaussian functions of spatial location x, and the transformed Gaussians are Gaussian functions of frequency k. The original center Gaussian has a width about 2 sigma c, and this width is smaller than the width of the surround Gaussian. The Fourier transform takes the spatial width from the denominator to the numerator, and similarly for the surround Gaussian. So a thinner Gaussian transforms into a fatter one, and vice versa. This is the well-known uncertainty principle. The smaller uncertainty in space gives a larger uncertainty in frequency, and vice versa. Let's ignore the negative frequencies, since they are just mirror images of the positive frequencies. Then the net contrast sensitivity function is this one. In the literature, this function is typically plotted using log-log axis, and as we expected, this function peaks at an optimal frequency. In physiological experiments, one can measure the shape of the receptive field Kx of a neuron by stimulating different spot locations X of the visual field and see how the neuron responds. One can also measure the contrast sensitivity function Gk of a neuron by showing gratings at different frequency k and see how the neuron responds, and also see at which phase value theta of the grating for each frequency k is the best to excite the neuron. And these two methods are related or interchangeable, and when the neural response is approximately a linear function of visual inputs. Once you have the receptive field shape Kx, you can get the contrast sensitivity function Gk through this Fourier transform. In reverse, once you have the contrast sensitivity function Gk, you can get the receptive field shape Kx through this weighted summation of cosine waves. And this process is called the inverse Fourier transform.